Hi, I'm Roland Minton. These are some of my favorite math stories. In this episode, Mathematics is Pigeonholed. We'll work with a simple mathematical principle and use it to solve some puzzles and decipher a magic trick. The Pigeonhole Principle is easy to understand but surprisingly useful for solving problems. The idea is that you have items with a certain number of categories, and you have more items than categories, then at least two items have the same category. The name comes from pigeons arriving back home. If there are 6 holes and 7 pigeons, for example, 2 of the pigeons will have to share a room. Not hard, right? Well, unless you're one of the pigeons cramming into an already occupied hole. Well, here's a simple example. There are 4 suits in a deck of playing cards. If you have 5 cards, at least 2 of them have the same suit. Almost common sense. More cards than suits, you have to repeat a suit. Now this is the basis for a clever mind-reading trick, which I of course learned from the great Art Benjamin. The magician has a volunteer pull 5 cards randomly from a deck, looks at them briefly, and then casually lays them down like a 5-card stud poker hand. 4 of them face up and 1 down. I enter the room and, using my poker skills of divining the whole card, name the face-down card, in this case the 7 of spades. Well, how does this work? I start by looking at the card as far from the whole card as possible, the 5 of spades here. This card and the whole card share a suit, so I know there's a spade face down. I then look at the other face-up cards and classify them by value. The 2 of hearts is lowest, the 9 of hearts is the highest, and the 4 of clubs is in the middle. The magician and I have agreed beforehand that the pattern low, high, middle codes for the number 2, and 5 plus 2 is 7, so the face-down card is the 7 of spades. The magician, I think, has the hard task here, although I have messed up the reading of the cards a couple of times. How do you casually and quickly lay the cards down to code the card correctly? Well, first you know that you will have at least 1 repeated suit. Why? The Pigeonhole Principle. 5 cards, 4 suits. So get 2 cards of the same suit. To get from one number, 1 through 13, to another, allowing wraparounds, you can always make it one number plus 6 or less, and there are 6 ways to order small, medium, large. For example, if you have the 5 and 7 of spades, 7 is 5 plus 2, so put the 7 face down, the 5 on the other end, and code for a 2 in between. It gets tricky when you have, for example, the 10 and 3 of spades. In terms of the deck, 3 is equal to 10 plus 6. Starting from 10, Jack, Queen, King, 1, 2, 3. So put the 3 face down and code for a 6. I usually use high, middle, low for that. Very clever. So here's one set of codes. Let's solve some math puzzles with the Pigeonhole Principle. Choose any 20 numbers from the list 1, 4, 7, 10, and so on, out to 97, 100. No matter how you do this, 2 of your numbers will add up to exactly 104. Well, how could you prove that this always works? The trick is to create categories that help answer the question. So categories 4, 100, they add up to 104, 7, 97, 10, 94, and so on out to 49, 55. Each pair adds to 104. These are all of the numbers in the original list except for 1 and 52. When you choose your 20 numbers, at least 18 of them will be from the categories. But there are only 16 categories, so by the Pigeonhole Principle, you must choose 2 numbers from at least one of the categories, and those numbers will add up to 104. Here's another one. Take a 2 by 2 square and choose 5 points inside the square. At least 2 of your points will be closer together than the square root of 2. How do you prove that? Since we're choosing 5 points, we probably want to set up 4 categories and use the Pigeonhole Principle. So divide the square into equal fourths, and each category is then a 1 by 1 square. The diagonals of the square represent maximum distance apart, and that distance is the square root of 2. So any 2 points inside a square will be less than square root of 2 apart. But with 5 points and 4 squares, we will always choose at least 2 points in the same square. They will be less than square root of 2 apart. And another one, suppose there are 20 people at a party. Some of them are friends with each other and some aren't. Prove that at least 2 people have exactly the same number of friends at the party. Well, the possibilities for numbers of friends are 0, 1, 2, out to 19. Oh, well, that's 20 possibilities, and we're choosing 20 people. But wait, if one person is friends with everybody, then there can't be a person who is friends with nobody. So the choices are either 1 through 19 or 0 through 18. So you've got 20 people and 19 choices. By the Pigeonhole Principle, there have to be at least 2 people with the same number of friends. One more example. It's a little harder, and the use of the Pigeonhole Principle a little less obvious. I'll use the numbers 4 and 8 in this problem, but you could replace them with any numbers n and twice n, and the result will be true. Start with the numbers 1 through 8, divide them into 2 groups, A and B, of 4. Arrange the numbers in group A in increasing order, and the numbers in group B in decreasing order. Then the sum A1 minus B1 plus A2 minus B2 plus A3 minus B3 plus A4 minus B4, always choose the positive version, the absolute value. That will equal to 4 squared, which is 16. As an example, suppose group A gets 1, 3, 6, 7, and group B gets 2, 4, 5, 8. Then we're going to order them as 1, 3, 6, 7 and 8, 5, 4, 2. B goes in the opposite order. And we'll compute 8 minus 1, 7, 5 minus 3 is 2, 6 minus 4 is 2, 7 minus 2 is 5. That adds up to 16. The key fact is that in every pair in the computation, we have one number from the 4 smallest numbers, we'll call it S, 1 through 4, and one from the largest set, L, 5 through 8. How can we prove that this always happens? Well, suppose, for example, the second term, A2 minus B2, contains 2 numbers from S. Well, A2 is the second smallest number in A, and it's in S, so there are at least 2 numbers from S in A, A1 and A2 at least. B2 is the second largest number in B, and it's in S, so there are at least 3 numbers from S in B, B2, B3, and B4. That means we've chosen at least 5 numbers from S, which only has 4 numbers. By the Pigeonhole Principle, that means we chose one number twice, which is against the rules. The same logic shows that both numbers can't be from L, so every term A2 minus B2 has one number from S and one from L. The L number's larger, so every term is an L minus an S. Adding them all up, we get all of the L's minus all of the S's, which makes, in this case, 26 minus 10 equals 16. Another way to do this is to group A with 1, 7 with 2, 6 with 3, 5 with 4. We're adding up 7, 5, 3, 1, and that's 4 squared equals 16, which uses the neat fact that adding up the first n odd numbers always equals n squared, which is the sum for any 2n numbers arranged this way. The Pigeonhole Principle isn't so much a magic formula as it is a line of thought that sometimes pays off. Sometimes problems require counting or separating items into categories. And that's what math does. It arms you with a wide range of thinking skills.